Okay, so welcome to lecture 14, and lecture 14 will complete our discussion on interfacial energy. So, in case of solid vapor, we have calculated how to calculate interfacial energy or surface energy from the book and bond concept. And then in case of solid liquid, we have seen that we can use some empirical formula, assuming that the bonds are not completely broken, it is a half broken. And we have used one formula which is 0.45 del H m, which is the melting enthalpy divided by the Avogadro number. And then going through the same route, that number of atoms per plane, and getting the value of solid liquid interfacial energy. In case of solid interface energy, we can also use some of the empirical formulas. Those formulas have come after doing calculations and experiments. So, we will come to that when we talk about solid transformation. Now, whenever we talk in this particular lecture, we talk about the physical concept of interface energy. So, where from this energy is getting evolved from thermodynamic concepts or ideas. And then once we finish this, then we will get to the heterogeneous nucleation. Heterogeneous nucleation. So, first let us get to the interfacial energy. So, we have seen that the interface energy, so it is actually in case of solid vapor, so all the bonds are broken, but in case of solid vapor the bonds are broken. In case of solid liquid solid, half broken bonds. Now, those are leading to some energy which is positive definitely, because whenever we are considering broken bonds, they are giving a sense of positive nature. Now, if we come to say the solid liquid or this, in case of solid vapor, definitely it will be a kind of flat interface because all the bonds are broken. Now, in case of liquid solid, it may not be completely flat. There could be nature that solid to liquid transforms in a gradual fashion. So, the interface could be, instead of this flat, it could be like this. So, if we see this the parting line, so interface could be like this. In some portion, some of the solid, if we see this is the solid surface, this is the liquid surface, some of the atoms in the solid, they have gone into the liquid phase and leaving rise this trough, and some cases, some of the portion they could not break open from the solid surface and they could not go to the liquid. So, if we see this particular section, so these are the part of solid and interface is not flat, and that time we call this interface as diffuse. Diffuse interface. Now, at the same time we have done our exercise how to get to the information of free energy of liquid and free energy of solid from enthalpy of solid as well as enthalpy of liquid. And we have seen that if we try to draw the G as well as temperature, we have seen that this is my Tm, this is Gs, this is Gl. This we have seen. and we have seen that at this point G S equal to G L. Now, if I try to see if we do another axis, and that axis, if we consider this is the distance axis, distance across the interface, which is distance across the interface if we do another axis, and if we try to see what is the situation there at along that particular line if we fix the temperature. So, that means this Tm is fixed. So, then if we try to see the variation of G across this length, we would get some idea about the physical nature of the interface and where from this positive factor of interface is coming into our picture. Now, we have seen another information what is that is basically if we see the H as well as S variation, we have seen that the and this is across temperature. So, then so we have seen that this information, this is 298 Kelvin for H S and this is H L, and H L is higher than H S, and similarly this is S SL and this is SS. So, solid interface, sorry, it is just reverse, this solid, this is solid, this is liquid. And now, from that, if we see the, this is basically my del H M and this is G S, this is G L, and here we are getting this G S. For example, if we draw this G L with free energy of G L with yellow line, and these we are getting by deducting minus T S liquid term. Similarly, if I try to see how we are getting G L from H S, we are deducting T S term. Now, this is at melting point. So, here G S equal to G L. Here also we have seen the variation of H across temperature. So, this is liquid and this is solid. So, there is a jump which is del H M and this is my T M. So, at T M also, if a solid transforms to liquid, so if we have both the existence of solid and liquid at T M, so liquid entropy would be higher than the solid entropy, as well as liquid enthalpy would be higher than the solid enthalpy, and this is liquid, this is solid. Now, if we try to plot them across distance, if I try to plot H as a function of distance across the interface, and if we consider that the interface is diffuse, so that means diffuse interface means the transformation, the liquid atom and the solid atom, they are not separated with a flat boundary, rather in some portion liquid has percolated into solid and some portion solid had gone into the liquid. So, the transformation region of solid to liquid. So, if we consider this is the solid portion, this is the liquid portion, this is the solid, this is the liquid. Within this zone, we have existence of both solid and liquid. So, this interface is having a particular a length. So, it is not a single line, there is a particular width of that particular interface. So, now if I try to see how the variation of solid and liquid enthalpy distributes in this across this distance at Tm, this is I am doing at Tm. So, that time we will see that if this is my solid part, let us do it here. If this is my solid part, this is H s, and the liquid part would be, this is liquid, this is completely liquid, this is completely solid, and this is the interface region which has a specific width. And if we try to see that the liquid enthalpy would be a little higher, but in between there is a gradual increase of solid enthalpy to liquid enthalpy. So, this is like this. Now, similarly, if we try to see what is the variation of S, or rather if I try to see what is the variation of minus T s. When I am talking about minus T s, this T is nothing but minus T m s, because we are considering that entire this distribution thing is happening at T m, and it is basically this point, but across this axis which is distance axis. Now, that time, since we know that the solid entropy is higher than the liquid, solid entropy is lower than the liquid entropy. So, if we multiply with Tm, both the thing would increase of the order of Tm. But if we put a minus sign, these Ts term for solid would be more than the Ts term of liquid, because we have considered a negative sign there. So, that time if this is my minus T s T m s s term, so the T m s l term would be lower than this, and the variation would be gradual from T m s s to T m s l. So, the T l is higher than T s, and that is why minus T m s s would be higher than minus T m s l. Now, if we see the variation of G L across at this point, so they are same. They are same. So, this is G L, this is G S. So, both the things are same, because that is what we are getting equilibrium. But across interface, and at the same time if you see that at this point would be H s minus T m s s, and here H l minus T m s l is basically G l, and this is G s. Now, interestingly, if we subtract T s term from T s term from H term, you will see that across this interface, this G s is not going to be G l. So, they would have a positive energy hump. So, this positive energy hump is coming due to the generation of interface, and these particular region is giving a positive contribution if interface is formed. Now, we can realize that even if at T m I have similarity, we have same GS and GL term because we know that delta G equal to 0, but if there is any interface formation that would have positive contribution, and now if there is a positive contribution and if let us say some solid forms, it cannot remain there because it is unstable formation, it is not possible. It is not possible because there is an increase in free energy. So, the transformation is not possible. So, that means at melting point no nuclei is possible. Rather, what would happen there, as we have seen in our discussion, if you see this particular variation delta G r as a function of r, those particular points would be always lying left side of this. So, that means as a function of r, there could be lot of solid like clusters, okay, but they cannot go beyond this, because all the cases I have positive contribution of interface, and this interface will not allow the free energy requirement for the nuclei formation, stable nuclei formation. So, now we can clearly see that interfacial energy is actually giving a positive contribution to the overall energy scenario. We wanted to understand that particular situation, that what is that interface energy. So, what is the physical essence of interfacial energy, and this talks about the physical essence of interface energy, and this is from thermodynamic principle, and this is coming due to the difference between H and Ts term. Okay. So, now from the overall discussion of this, we get to know why interface is so critical. And you might have noticed in our previous calculations, we have solved one problem where we mentioned that if interface energy increases by 10%, what happens to the nucleation frequency or the nucleation rate? We have seen that the nucleation rate goes down to a great extent, because this nucleation interface energy always acts positive towards the overall energy contribution, but we need negative contribution. So, that means the negative contribution is coming from either you get rid of interface or you add a volume free energy to it. So, that would decrease the free energy, but if you have interface creation, that would always increase the free energy. So, that is not a requirement for nucleation formation. So, I think we will start our discussion on heterogeneous nucleation in our next lecture, because once we start this, we would have to interrupt it in just 2 minutes time. So, let us stop our discussion on this, but I would request you to go through those diagrams, and I would also request you to plot yourself. So, if you do not plot yourself, so it will not be sufficient to understand the entire subject. So, when you solve, you will have lot of queries and get back with the queries. So, it will also give a lot of sense to float this for this course. At the same time, we will have lot of interactions too. Thank you very much. We will start our next lecture, and in the next lecture we will talk about heterogeneous nucleation. Thank you very much.